Donc, bon après-midi tout le monde, merci d'être là. Je vais faire mon exposé en anglais si ça pose pas de problème. D'accord. Okay, so I'm Isabel Amigo. Again, thank you for being here. I'll be presenting part of my thesis, ongoing thesis work, which is mainly about pricing mechanisms for assured quality services in a community of autonomous system or network service providers that we call alliance. This work is based on publications along with my advisors' thesis. First, please let me rapidly introduce myself through the two main aspects I have been conducting my thesis work. Actually, I'm doing the thesis in a quote-to-advice fashion, that is to say that I spent some time in the University of the Republic in Uruguay, where we work in a joint research group with the electrical engineering department and the mathematics department, through different aspects, mainly through analysis and modeling of telecommunications networks, economics of multi-service networks, and measurements and statistical learning applications. The collaboration between Universidad República and Telecom Bretagne, here in France, in West, where I'm doing the other part of my PhD, that dates from a long time ago. Some examples of this collaboration, it's the METRE project, which it's about monitoring, analysis, and traffic engineering in heterogeneous networks. It's a joint project between Uruguay, the Universidad República, Argentina with the UBA University, here in France, Telecom Bretagne, and last CNRS. It has started in January 2011, and we will be finishing soon, this month. So I have already told you I'm in this co-advice program. I have been previously another student that has already finished his thesis, and both of us under the direction of Sandrine Baton and Telecom Bretagne. The second axis that has been driving my research studies is the ethics project. Ethics is a FP7 project, so from the 7th framework program of the European Union, where 17 partners are involved. Ethics comes from economics and technologies for inter-carrier services. It has started as well in 2010, and it's about to finish next month. In particular, the project, from its name, it says quite a lot, but its objective is to create a new ecosystem for QoS-enabled interconnection model between different network service providers, and where fair distribution of revenue shares is achieved among all the actors of the service value chain. In particular, in this project, we have been working in different aspects. Just to say briefly, some aspects regarding service monitoring, some aspects regarding the economic aspects, where mainly this talk is focused. That is, that we have proposed an alliance framework for selling services and subsequent revenue sharing among the members of the alliance. And we have also been involved in the dissemination work package. So, more in particular, the objective of this project, and which is very closely related with my research work, is to provide a new assured service quality architecture, which will handle several issues that we have identified. In particular, more from the economic aspect, there is some asymmetric information in the market. That is to say that buyers, the clients, when we want to buy one service with quality, we are not really sure about the quality we are going to get. This makes that indeed it leaves the good quality products or services out of the market in the end, because we tend to think that things don't work that well. Also, the business models that rule the internet nowadays may not satisfy all the involved actors. Roughly, we have from the business rules, I'm talking about the customer-provider agreements, which are based in some per traffic pricing, while at the same time, the network service providers charge their users in a flat rate. We are used to paying flat rates, and that's all. But then they have to pay for the provider in a per traffic rate. And then we have also the peering agreements, where there's some assumption of symmetry in traffic. But that's no longer true. For instance, when we are watching online videos, there's no that symmetry in place. So also we're not paying for quality. These agreements include quality pricing, so they might be a lack of encouragement to provide this quality of service among the providers. And there are also some other problems about inefficient routing when there's congestion. I'm also working in the multi-domain end-to-end framework. That is when several domains are involved. What we have identified, one of the possible solutions that this project has come to is the alliance solution. It's one of the communities that they have defined. Actually, there are different levels of communities, and the alliance is one of them, which mainly tries to get together, to make the network service provider to collaborate among them instead of compete, in order to provide these end-to-end quality assurance services. For making it to work, we need some new business rules to be in place. I'm going to talk shortly. And why putting this alliance as well? To provide these end-to-end services, to provide some synergy with the idea behind of increasing the revenues and the market opportunities of the members involved. And well, also some more intuitive benefits, that is to increase the number of clients to which they can reach, and also the geographical coverage. To slowly put this more into earth, some of the rules have been defined in the project to these alliances. The rules go from more business to technical rules. What would be important for these alliances is to have joint business rules regarding the pricing mechanism used, the revenue sharing rules or principles they will put in place, and also they will have some agreements for providing quality, for which they will pay penalties if they are not achieved. Also, they will have to agree to have some level of trust and confidentiality, because in order to have common allocation rules to be more efficient in traffic allocation, they will have to share information about capacities, about interconnection points, or different aspects that till nowadays providers are more silent don't want to share with some. Also, another important rule that has been established in the context of this project is the necessity of a monitoring infrastructure. In particular, well, I've already said, my thesis works around the technological and economic aspects of these alliances. I started in March 2010 and I'm planning to finish in a couple of months. And I have focused in 3 different axes of these alliances, of these technical and economical things. The first one was about interdomain QoS path composition, that's to say how we build these paths in order to have end-to-end reachability with quality, where BGP may not be enough. How we sell services, how we allocate the traffic to the paths that we have computed in point number 1. And finally, how the revenue is shared among all the domains involved in this alliance. In particular, in this talk, I will focus in this last point with some introduction to about the second one. So let's put this a little bit more into equations and not that much in words. And let's see the technical part of the talk. I will first define the alliance model, where we have done some abstractions in order to be able to work with a mathematical model. Then we will go rapidly through one with allocation problem, and finally the revenue sharing problem. Well, in the alliance model, as I've already anticipated, we have this autonomous system of our domains that are going to be work together, which are represented by these clouds, where we are going to abstract each one of them by a node, which we will call small n, and they will belong to our set of nodes of the Grand Alliance, and it's capital N. Each node, domain, now node, will have some equivalent capacity that we will represent by Cn. And it's the abstraction of the capacities of the resources that the node can provide to this alliance. Over this alliance, we will sell some services indexed by small s, and these services belong to a set capital S. We assume in the hypothesis that these services are sold over fixed routes are computed in advance, and we will call them R of S, the route of service S. Finally, for these services, there will be some users willing to buy them. These users may not necessarily be the final user, but big content providers or other also connectivity providers that need some quality to sell afterwards, to deliver their content with high quality. Well, we assume that for each service there is some willingness to pay. That's the money that the user will pay for the service. And looking at that from the network point of view, that it's a function that we call utility, which is a function of the bandwidth allocated or accepted for that service. That is to say that the price that the alliance will receive for each service is a function of the bandwidth accepted on that service, and it's represented by this function US of AS, where A is the bandwidth accepted for service S.
Just a
yes.
question. For the routes, so there is no choice between different routes. For one service, there is a compulsory route. You cannot choose it according to the utilities.
Exactly. For the moment, yes, or in this presentation, for the user, a service will be some chunk or amount of bandwidth with some quality associated, which goes from an ingress point to an egress point. We will not care about the route, and in our model, so far, we will consider just one route. Although the first path can be extended to multi-routes. I will just present it to multi-path routing just from one path. Any question? Okay, so finally, how are we going to allocate this bandwidth? We're going to decide where to sell the services in such a way that the revenue of the whole alliance, because they are collaborating, so all of them, is maximized. We have some constraints, that is, we can't transpass the capacity, the equivalent capacity of each node. And then we have also some quality of service constraints, that it's end-to-end thresholds that can't be exceeded as well. So let's go to the phase of the bandwidth allocation in this case. So we're going to address how we maximize the revenue of the alliance. In particular, we are proposing, I've been talking about this utility function, that is the willingness to pay of the buyers. We are going to present this with an application that is using first price auctions. Actually, the price for selling these services, these enhanced services, may not be known. They're quite good new services in the market. So instead of the seller proposing, or the alliance proposing some price, we're going to decide the market to lead the market, decide the price through the use of first price options. In general, this first price options is just just each of the buyers will propose an offer, a bid, and the highest bid will win the service and pay the amount offered in the bid. That is in the simple case for one service. Here we want just to change a little bit because we want to accept the bids that maximize the whole revenue over the different services on sale. Let's put this onto app. For each service, we are going to sell a chunk of bandwidth. And each service will be associated with a chunk of bandwidth that is called sigma S. That's what each buyer will get from the service, and depends on each service. And several instances of that are going to be sold for one service. That is to say, several chunks for one service is going to be on sale. For each service, we suppose that there is a certain number of users that are interested in getting this service. This number is given by NS. So for each service, buyers made their bids, and we're going to order them from the highest to the smallest one. So we have NS bids, and we will call them BS because they depend on the service, and order from the first one to the smallest one. With this information for each of the services, we will be able to construct, to build our utility function I mentioned in the previous slide. How? Well, if the utility function is that it's a function either of the amount of bandwidth accepted or the number of bits per service, because per bit we have a definite amount of bandwidth that it's sigma s. And since we have ordered the bits here in this graph, let's mention that here is utility and here are the number of bits that are accepted. The first one will give us a revenue of BS1, the second BS1 plus BS2, the third, the sum of the three highest bits. And like this we're going to build our concave function, but actually it's only defined for discrete points. So we're going to extend it to a continuous of values of bandwidth just by linear interpolating between the points. And finally, the utility function then is defined just as the sum of the ordered bits from the first one to the accepted one, to the last accepted one.
I'm sorry, do they
Yes.
make bits and also ask for quantity? Or
Actually, the idea is that it works a little bit the other way around. There is some catalog of services which publishes the services, and each service is defined for a given amount of bandwidth. For example, we can think about if some services are thought for video, we think about which bandwidth is needed, if they are needed for voice, and the sigma s is predefined, and the BIOS will choose the one that suits their
Yes,
size.
so one byte might be buying multiple chunks of bandwidth for the same service.
Why?
I have a video which is a low rate video and a video which is a high rate video. So how is it handled?
Okay, actually we can have different services that share the same route and that they are characterized by different things. For example, they share the same route, same ingress and egress point, but the amount of bandwidth is different, and the threshold of the quality of service parameters is different. We can afford that. Was that the question?
Sigma s is not a system-wide parameter. So
It's per service from end to end.
Okay.
Per service, exactly. Yes.
And the bits are for the sigma s or for the service as a whole? That's not clear.
For the sigma s, actually what I call service is this abstraction characterized by an ingress and egress point, a route and an amount of bandwidth, and the QoS parameters. So for each service, this characterization, we can sell several chunks, and different users can build for them.
It's just that in the notation you don't see in the bit the sigma s, you just see the service. It's always not so clear.
Okay, because there is a map between one service has defined sigma s. It can allocate several, but it's
Okay.
defined.
and why the first byte option and not big rectangle blocks, or I don't know,
Yes.
kind of option, optimal option?
Okay, that's a good question. Actually, yes, in the literature, the previous proposals, mainly there are some proposals with first price auctions, but mainly propose second price auction. That is that still the highest price wins the auction, but the price paid will be the second highest price, or victory auctions. Actually, what we saw about that, well, they use that by auctions, claiming that they can obtain the real value of the service. I mean, the behavior of the buyer, the better behavior is to announce, or the best behavior, to announce the real value of the service. That's the motivation behind using second price auctions. In our case, what is more interesting is to maximize the revenue of the alliance. We really don't care
So,
about the
yeah, but in that sense, Meyerson would be Meyerson maximize the expected value.
the revenue of the seller, I mean of the whole
Yeah.
square thing. There's a second motivation for us to use first price actions. That it actually is much more easier for the buyer to proceed, because the previous proposals using the other actions needs need more knowledge from the buyer. That is, for example, placing some bits for each link, having some knowledge of the topology. And we're thinking about buyers that just interact maybe with a portal or something and they don't want to know anything about topology. So that's the main reason why we went for price options. Question? Okay, so we have said that we want to maximize the revenue of the server or the alliance. That is just a maximization problem where the objective is to maximize the revenue. Here we have our utility function summed up over all the services provided by the alliance. I have introduced a new function, if you can see there, QS. It's just a function that represents the cost that may have to carry that service of that amount. And it's also a function of the allocated bandwidth. And it's assumed to be a convex function, one for each service, just to take into account also some cost. Then we have different restrictions that I have rapidly talked about them before. The first one, equation number 3, cares about the constraint in the capacity of the nodes. We can't overpass the capacity of each node. So all the bandwidth traversing one node needs to be smaller than the capacity of that node n. This is valid for all the nodes. Then we have quality of service constraint. We are assuming an additive metric from n to n, and we're assuming for each service, this new function dn accounts for the delay of traversing node n. And it's a function of the whole bandwidth traversing node n, not only the one for the service, and the capacity of that node. And it's additive, as I already said, so we're adding in all the nodes that compound the route R of S of that service S. Then the S is the parameter characterizing the maximum value of the delay, in this case, for service S. And this has to be valid for all the services. Yes, sure?
There is a A. What is A?
Yes, A, actually it's a vector.
It's a vector, okay.
It's a vector of all, yes, so it's not written here.
Of
All the AS, exactly, of all the bandwidth. That's just to represent that the delay depends on all the whole bandwidth traversing the node and not just the one concerning the service in question. The last constraint, number 5, accounts for actually, instead that we're accepting clients or bits, so this is an integer number. We can't accept 2.5 clients. So we are just saying that the total amount of bandwidth accepted from one service over the chunk, the value of the bandwidth for that service should be an integer, actually, for each service. So this will be the general problem we want to solve. But we're going to move to a simplified formulation in order to keep on working, where 3 different remarks had to be said for this simplified formulation. Q of S, the convex cost function, is no more over there. That's actually not a problem because we're still optimizing, maximizing a concave function. So it's just to the sake of simplifying notation. Then we have written of the capacity constraint. What we are assuming is that the delay function of traversing each node, dn, it's a barrier function. That is to say that when the amount of bandwidth traversing node n approaches the capacity of that node, the delay goes to infinity. The function dn goes to infinity. So that's going to be enough to keep a solution aware from trespassing the capacity. And finally, we're not having any more the integer constraint, since optimizing over that kind of problems is known to be NP hard, so we're accepting suboptimal solutions. That is that we're going to solve the problem allowing AS to be just a positive real, and then we're going to round down the solution. Okay. Now, in order to solve this method, well, it's actually a classical optimization problem. We have a concave function that we want to maximize, but we want to do this in a distributed way. That is to say, we don't want to submit all the bits of all the services for the whole alliance to a centralized brain that computes and allocates the bandwidth, because we're thinking that this could happen in a timescale that is much faster than what would be needed to solve the decentralized solution. So we are proposing a gradient method where we have to do some updates in the primal and the dual variable. The primal variable being the bandwidth, AS, so the whole vector A, and the dual variable, the Lagrange multiplier, noted here with lambda S, one for each service. Just let me go backward. We have the constraints, one per service. The idea is just to compute this on the gradient method, so updating each of the variables iteratively. I'm going to call source node of a route, the first node in the route for each service. This node is going to start from initialized values for both variables. It's going to send the values AS and lambda S down the route of that service, and each node in the route is going to receive all the concerned values. Then each node will have to compute this term over here, that it has received all the bandwidth, the values of AS traversing the node, has received all the values of the lambda concerned, and it has to compute, that node has to compute the derivative of the delay times the lambdas and send it back to the route, to the source node, to the head of the route. In addition, each node will compute with the same values, A and lambda, the delay of traversing the node, and as well send it back to the source node. When they send all this value back, we're going to accumulate the values, and just one value is going to arrive to the source node, which in turn is going to update the values of the variables and start the procedure again. And this can be proven to converge to the optimum of the simplified problem I just showed you in the previous slide. Just a remark that the DFC is to happen at the control plane level. I mean, no traffic or no bandwidth is allocated till the convergence of that. It's just the numbers that go back and forth. Okay. So
this is in general, I'm sorry, this is
yes,
in general
yes.
dynamic, no? In general, you ask for services in some locations. So how could you incorporate that into your, I mean, I don't know, if I want to connect to see a movie in Netflix.
Okay, I see. Maybe one approach could be that there is this portal, this webpage that receives the bids that manages the auction and decides, okay, in 5 minutes this one service is starting and we're going to receive. I mean,
Like in the electrical market, something like that.
something like that. That could change a little bit if we're talking about final users, or if we're talking about big users that compete for like a big pipe. Yes, it's true that we'll need some coordination for when the service is going to start. Yes. Yes.
So you may talk about convergence later, so in this case, just to be later, but if you have multiple services that are required, they share a path at a given point in time, they might have mutual interdependence because the delay on a path may grow because there's one service that if agreed, then will raise the delay on that path because it raises the amount of bandwidth which is used. So how does this affect convergence and how many iterations are needed typically? So can you comment on that?
Okay. Yes, I will not go further in conversion, so we can talk about that now. Actually, well, the first problem that we have solved as a previous work with multipath was with capacity constraints and not with the end-to-end delay. And in that case, it can be proved to converge. I mean, analytically proved that it converges. We didn't work in optimizing the convergence time and we're sure about convergence. And then about the convergence, I'm trying to remember how far we got from there. Yes, okay, so the proof of the multipath for the capacity constraints can be extended to the delay constraint as well, but we haven't worked on tuning how fast the conversion, we just have seen that. It would be also interesting to implement it, and not only we have simulated it, and see how that works, and also the possible as not synchronizations within there. But we have not continued that line. Yeah. Question? Okay, so far how we are envisaging to allocate the bandwidth in the alliance. And we will now move to the second part, how to all this allocation, provide some income to the alliance, how we are going to share it. Let me first say some words about why we want to do this and how we are going to do it. Actually, there are two main motivations to do to perform the revenue sharing. Both are quite intuitive, I think. The first is that in any activity or work that we are doing in a cooperative way, it's quite natural to suppose to share afterwards the costs or the revenues in a fair way among all the involved actors in every aspect of life. I mean, we make go eating out together. We want to finally we're going to decide how it's going to be split. And we are all collaborating. We supposed to do it to share costs or benefits in a shared way. But it is also a way to incentivize or to encourage the actors to behave in a certain way. If someone spends less, then it's going to have to pay less. That it's kind of incentives to provide them in order to behave in a way that we want to apply. And we're going to see this shortly. Also, how to do it is not that evident because there are different criteria that may sound fair and that provide different shares. Let me just say a small example that it's quite known, that is the contested determinant. That we have two persons, they're called A and B, and they want to share a piece of fabric. Person that we have called A just wants half of the piece, and B, which we're going to represent with the yellow, wants the whole piece of the fabric. Okay, so which is the first way to share it? Which part do we give to each of them? We can think about different rules. The first one, or a common one, is the proportional rule. That is to say, proportional to what they are asking for. Just bearing in mind that we need to sum up. We have just one piece of fabric, we can share more or less than that. So if we normalize by the total demand, it turns out that A will take 1/3, and B will take the yellow one 2/3 of that third. Maybe this could be a fair way. There are some other proposals, like what's called the Talmud law, that's actually suggested in the Talmud. And actually says, well, there's one person that wants only half of the fabric, and the other person that wants the whole fabric. So actually it's only one half that is contested, that both want it. This first half only B wants it, so we're going to give it to B, and we're going to split the remaining, the contested part, equally into two. Half and half of the resulting for A and for B, which turns out to give 1/4 for A and 3/4 for B. Is this fairer than the previous? Yes, maybe not. I mean, just the point is that we need to agree in the properties we want to fill and how, because if not, we can have many answers to the problem. What is different in our problem from this is that the revenue that we want to split is not something fixed and something that depends from the resources of each of the actors in place. Here we are not talking about demand because there are no costs. In our problem, we are more talking about resources that each of the domains of the nodes that I have been talking provides to the alliance, each of them. So it's a little bit different, our revenue, because it's a function of these resources. So let me redefine the income function. That actually it's given by the bandwidth allocation phase. So we have already defined it. It's only that we will need some little more notation. So the revenue function, which is going to determine the whole pie we want to divide, is going to be called V, and we'll let this function depend on two parameters, Q and C. C is the vector of the nodes capacities, equivalent capacities that we have defined. And Q, it's a subset of nodes belonging to the ground coalition and the alliance that we had. We're going to define this function. We're going to see shortly why we need to also make it a function of all possible subcoalitions. But just from the previous problem, by considering a definition for each of the possible subcoalitions. That's why we need to introduce SQ, this set, that it's the set of services that can be provided with a subset of nodes Q. Okay, we have assumed that routes are fixed. If we take some nodes out, some services are going to be taken out as well. I think that's all that we have changed here. Yes. So let's do
for every coalition, for every possible coalition?
For every possible coalition, we need to. That's right. So with this revenue function in mind, let us review some of the basic properties that we think that revenue sharing method in this context should fulfill. Just two more notation for the moment. BI is going to represent the contribution of node I to the coalition, to the alliance, the contribution in terms of revenue. And it's going to be defined, this one is quite intuitive, as the revenue of the whole alliance, B of N, minus the revenue of the alliance without node I. So, and we are not considering node I. Here I didn't put the dependency on the capacity because just to simplify notation, but it's implicit the capacity vector in that function B. And then vector X, which has the elements equal to the number of nodes in the alliance, is going to represent the share of each of the nodes in the alliance. So Xi is the share that will go to node I on the right. The first, into the property we want to fulfill is efficiency, that we just done the same thing with the fabric. We just have one total revenue, and we want to split it all, no more and no less of it, which with our notation can be easily written like this. All the vector X, coordinates, must sum up to the total revenue B of N. Let's then talk about a little bit about stability. We are in this cooperative framework, so we don't want to provide any of the NSPs belonging to this cooperative framework any economical incentive to leave, to break up the coalition, or to form subgroups with other members, which in the context of game theory, it's usually referred as the core of the standalone principle. So we're going to define this in mathematical terms as like the sum for every subcoalition. Let's consider one subcoalition Q of the ground alliance N. And for that subcoalition Q, all the shares of the nodes belonging to that subcoalition should sum up more than or the same at least, should sum up the value of that subcoalition Q, the revenue, B of Q. And this must be valid for all the possible subcoalitions. Just to give some intuition to the idea behind that, let's consider a subcoalition made only of node I. That is one possibility. That means that the revenue that node I takes should be at least the same as the revenue that he would obtain on his own. Okay, B of I. And this, we extend this concept to all possible subcoalitions. And then we have a property regarding what I anticipated a little bit, what we want to incentivize in the members of the coalitions. What we think is important is that it's what we call a resource incentive property, is we want to provide incentives to the different NSPs to increase, or at least not to decrease, the resources that they provide to the alliance. And then we can talk a little bit about fairness, which, well, I tried as well to anticipate a little bit, but in the literature there's not a common agreement about what fairness means. Actually, we've seen that sometimes depending on the rule proposed to the fairness, the kind of fairness they say that they fulfill, so it's kind of customized fairness. However, some concepts that are repeated along the literature are, for example, the order preserving one, which I found also quite intuitive as well. So it means that if we have two nodes, domains, that one provides domain I, for example, that provides more revenue, contributes with more revenue to the alliance than node J, well, then this order should be preserved as well in the shares. That node should receive more or at least the same as the other node. And in a particular case, the equal treatment of equals, which is the common name that we find in the literature, that is if two NSPs contribute with the same to the alliance, then they should receive the same share. And the last one here, that I interpret that one as like not allowing the free riders, that is if someone is not contributing with revenue to the alliance, then that domain should not receive any revenue. So I wanted to say anything. Okay, just an observation. Here, actually the resources that the nodes provide are modeled here as capacities. We are discussing here using the contributions because the capacities themselves are not that meaningful. I mean, it's important the capacities that they provide, but also where they're placed in the topology of the alliance. It's not that interesting having a great capacity, but not attracting any clients or not having many connections with the rest of it. That's why we decided to discuss the fairness using the VI, that's the contribution of each node I. Question? So, we shall review 3 classical methods and then conclude with a proposed method. The first one that I would like to show to you is the Shapley value, that it's a well-known concept in coalitional game theory, which proposes a way for splitting the revenues in general sharing problems as the one as we are addressing. The idea behind it is to assign a share for each node I, which is kind of the average contribution of that node I to all the subcoalitions. We can find that here in the formula. We observe this term together. We see that it's more or less the same definition as I define as contribution to the coalition, to the Grand Alliance, to N, of node I, but the contribution to coalition Q. So we have the total revenue of Q considering node I, and the total revenue of coalition Q. So that subtraction is the contribution of node I to subcoalition Q. And then it's just averaging over all the possible subcoalitions here. And we have some normalization terms. We can solve all the possible combinations here and here. And that's what the Shapley value rules determines for each node I. And it has standard properties. However, in our particular problem, it's not that interesting because it does not fulfill the stability property that we have just judged as mandatory, quite important, because we want to have some stability in the coalition, in the alliance to work together. Here I put just an illustrative example, quite simple example, to show in a concrete case why it's not working for our revenue function. We have this very small alliance made of 3 nodes and 2 services, S1 and S2. The bits and all that we have seen before, arranged in such a way that the optimal allocation implies a total revenue for the alliance equal to the revenue of selling only these services, so the alliance 2 and 3, which is of 5 units in the system. And it implies as well that the revenue of N1 and N3 is equal to 2. Then the other alliances receive 0, so I didn't put them there. If we want to provide a stable solution, then coming back to the previous definition, we need that for every possible subcoalition, the shares of that subcoalition must sum up at least to the value of the subcoalition. We just need to consider 2 subcoalitions that one have no revenue, One is this one, so let's consider first one, this one. So we find the inequality x1 plus x3 greater than or equal to 2. And if we consider the other superposition, we need to fulfill x2 plus x3 greater than or equal to 5 units. And then we, of course, we always want to be efficient, which was defined as splitting the whole revenue. So they should all sum up to 5. So in this system, really, we can conclude that the set of solutions fulfilling both properties, it's segment of line, which gives to node 1 0 revenue. However, if we compute this formula for this model alliance, the Shapley value formula, we obtain another allocation, which we can easily see that does not belong to the segment considered because it gives something to node 1. Sure. So this was just an illustrative example to show that in the general case, we will not be sure of providing stable solutions, so we are not going to use Shapley value.
Just a question.
Yes.
What does the Shapley value do? Because here it doesn't fulfill the stability property, but it should fulfill other properties.
Yes.
So what is the goal of the Shapley value? I'm not familiar with this.
Okay, that's interesting. First, two things. The first one, yes, here it does not provide with a stable solution, but however, it is proven that in the cases, in the games that are called convex games, that is where the revenue function is convex, it does provide with stable solutions. That's proved, what's proved by Shapley. So in that case, it's interesting. However, it has some other interesting properties. It's the one of the resource incentive that I had said. That is to say that if a node increases the capacity, then it is assured that the share it's going to receive is going to be at least the same share that it received before. Then there are some fairness also properties. Fairness defined a little bit customized for them. As that what one node contributes to another, it's equal to what that other node contributes to that. So there are some specific fairness properties defined. And yes, in many problems, cooperative games, it is indeed useful. But not in our case. Why? Because that revenue function defined after the optimization problem is not convex in C, like other resources of that problem. Let's move to this proportional rule that we're already familiar with that one, because it's intuitive and we have already seen it. And it can be extended to this complex problem. Again, we have used here the VI, so the contributions, and not the capacities, because splitting with respect to capacities was it's not meaningful, actually. The nice of this is that it's really simple, as we can see, it's to compute, but however, and maybe we can agree that it's fair as well, it's proportional, we could agree on some fairness properties, and we can arrange ourselves to have an efficient solution, but however, it doesn't fulfill either the stability property in our problem, and we will see that through a simulated example, so we can go on. Finally, there are some differential proposals. I will talk only about this one, the one proposed by Oman and Shapley, which the idea behind this is to consider the contribution in the resources, in the capacities, that like the differential contribution over all the possible values for each of the nodes. So here, let me just explain a little bit the formula. Delta I stands for the derivative of the revenue with respect to the capacity I. So in order to compute the share of node I, we're going to sum up, integrating in the limit, the differential contribution of that node in capacity to the total revenue through a particular path. So there are another rules that propose another integration path. This one, it's going proportional, so in a line with the capacity and the integration variables, which just propose to integrate in the line. We have two problems here that mean that we can't use it. The first one is that it asks for a general function and V, our function is not variable for all the values of C. And we can see this quite intuitively. Actually, the revenue depends on the bandwidth that enters the network. Okay? So if, let's consider a simple example where we have, I don't know, maybe that by some nodes, and they have all the same capacity C. Let's talk about the derivative of this node, that's node 2, with respect to his capacity. So if this node increases the capacity, then the amount of bandwidth that can enter here is not going to increase because these are acting as bottleneck. So the revenue will be the same and then the derivative there will be zero. If, however, he diminishes the capacity, we can still have some bandwidth, but maybe some A2 smaller than A1. We will have some revenue smaller than the other one, and we have a positive value for the derivative. So in the point it doesn't exist. Okay, I will carry up a little bit. So another comment that is important is that this one is not, this rule is not resource incentive. I actually can make the nodes to want to diminish the capacity. They want to be the bottleneck in the path to have more revenue, and that's certainly not what we are looking for. Okay, so let's finish with the reviewed properties, and let's go to the proposed method. We are going to do an axiomatic characterization, and actually it's really easy and fast to present because we are going to choose the efficiency and stability properties that we have said that they are the most important, and we are going to write them just as linear constraints. So we need to introduce matrix Q that represents all the possible combinations, and B hat are is a vector that contains the revenue of all the subcoalitions, so we just have rearranged that in matrix and vector form, and we can write the stability condition and the efficiency condition here. With these two linear constraints, we have defined a polytope. Actually, just let me remind you that each of the x should be greater or equal to 0. We are not accepting negative values. And we have defined a polytope, and which fulfill all the points over there, fulfill the stability and efficiency properties. Then we would like to choose a point in that polytope in such a way. So we propose in a way that provides us with some other properties. So we propose an optimization problem where we have introduced the criteria f of x, which is just any convex function that we will define in turn. And this will allow us to determine a point of all those that verify the properties that we want. In particular, we have studied different criteria, and other ones that I will just comment in these ones. First is a linear criteria, so let's weight each of the revenues by the capacity or by the contribution, E. Then we would like also a different criteria, could be trying to equalize the shares among, when possible, among all the nodes, so they should receive more or less the same. Or we could take other solutions, as the shape value or the proportional, and project them to our feasible set. That is to say, when they are not fulfilling, get the closest point over there. Just want to see three different simulations, just to briefly see what each of the criteria can provide. Rapidly, we see here we have an alliance of 4 nodes. All of them are carrying some traffic in the red services. And rapidly, we see that here we see for each of the nodes, where colors are corresponding, the share that each one of them gets for the different criteria. Linear ones are shown here, for example. We're just stopping this one in this case. And we see that they are not fair at all. For instance, with this linear criteria that is weighting each share by the contribution only gives some revenue to node 4, which is kind of not what we are looking for. The other properties, I will not stop, but the other criteria in this case are quite well Again, let's see in another example. In this one, if you remember when we talked about the proportional share, I told you that it was not stable in all the cases. This is an example of that. In this column, we can see the proportional share. And here, we can see the projection of the proportional share. And we see that they are not the same, so that means that the original vector is out of the feasible set. That's why the projection is different. So this is just to show you that we can't rely on that method. Finally, let's repeat the one from the shape of value that I have already shown you a small example. But here we see in this column we have the normalized shape value that is given some revenue to all the nodes involved, while only the ones with the red arrow are carrying some traffic, because it was the ones that were maximized. So shape value again is not a good one. The linear ones, no, either. But we can still rely on the projections of the other methods that are likely to provide some fairness. So just a word, and then we'll finish, about computation and cost. I have computed, and they have highlighted that here, and it's correct. We have computed the revenues for all the possible supervisions. That could be kind heavy. Actually, the cost is around the same of the shapely value that needs to do all the computations. Our proposal is to perform this revenue share for example, in a monthly base. I said that for revenue for bandwidth allocation, we need something that is more dynamic and that is done distributedly. However, in this case, we're talking about this alliance that is going to work together and have some centralized entities performing these computations in a monthly, for example, basis, because they're not going to be sharing, or as we don't bill at any every day of the question.
What is your order of magnitude of N?
Okay, that's also important. Well, for instance, that has been discussed a lot in ethics. You should know. We didn't finish with one answer, but we have been talking about the order of 10 ASs or something like that. Some partners have been proposing more. Actually, for instance, the main thing is that the largest path in the internet of the BGP path is no more than 4 ASs. So I think that we won't be talking about alliances that are really, really big. That N, in my opinion, will remain not that big. So now, yes, to conclude, we have discussed a little bit the possible emergence of the alliances of network service providers in order to provide quality of service from end to end. We have proposed a bandwidth allocation mechanism which can be seen as a network utility maximization problem, that maximization problem that we have seen. We have treated the revenue sharing problem for this kind of network utility maximization problem, that is to say when we have the revenue function given by that optimization problem. We have discussed some of the properties that could be needed for that revenue sharing method, and reviewed that the existing methods are not fulfilling those properties. We have proposed a family of methods. Actually, it's a family because it can be tuned through the function f, where we have shown through simulations that some functions are better than others. And finally, well, we would like to, I didn't discuss this here, but we could include in the constraints as well the resource incentive property, and that can be done. But it would be nice also to include it in not only in the constraints, but in the objective function that should be proved, and it's for remaining work. So I thank you for your attention. I apologize for time, and questions are welcome, of course. Yes, please.
Thanks for your nice talk. I have still two questions, or a couple of questions related to your model. I understand it's really targeting network service providers, but so on the one hand, you do not at all consider the fact that services can be hosted by third parties. Because then it changes a lot the model.
Yes, that's true. Actually, how I think more about it, it's like, for example, if we have some OTT or the top providers outside, maybe those are going to be placed as clients, and we want to deliver their content through a pipe that has some guarantee of bandwidth and delay or quality of service parameters. So yes, the service maybe it's like more abstract here. It's
So the other point, still related to the model, is very much similar to what Claudio mentioned before. Of course, I understand your quality of service constraint, but this is not really taken into account in the model, because this might fluctuate with respect to the solution that will be implemented or chosen by your algorithm. I mean, the delay on the path, I mean, how do you really, how can you really capture the delay on the path?
well, yeah, that's.
It's very abstracted in your model, so I don't know how you can really control this.
Yes, in the model it's quite abstracted, and when we have performed simulations, what we have done, for example, is use a very simplified model that we have at each node a delay, each node model as an MM1Q, and then we have this one formula for the delay of traversing that node, and then the end-to-end delay path would be a sum, just summing up all those. So that was what we used when we performed simulations. If we had to do it in real, we are asking the nodes, yes, to have some notion mainly of how the delay relates to the traffic that they
If I can, the last one, I'm sorry. Often the demand changes with respect to the cost.
Okay.
So for instance, if I want to access Netflix VOD, then if the content provider is increasing the cost, the demand will reduce because actually maybe I cannot afford it. I don't see this here. I mean, I saw your utility as a function of the resources that are required, but I don't see how the demand will evolve with respect to the cost.
Okay. I think that we should think about that. Actually, we could think of that as if the provider were imposing a minimum value of the bid, for instance. I mean, they're selling the service only if bids are over, right? The minimum price is, the reservation price is to 10 euros, for example. So yes, we will not accepting this, and we will not accepting bids that go under that one. I think that actually we didn't include in this model the behavior of the buyers at all. We just said, okay, there are some number of buyers, and maybe there are a lot, and if we increase the resale price, this minimum price, we will still be having enough clients. That's the main hypothesis behind, because since we're using these options, we assume that we have more clients or more price than the resources we have to sell. But it's true that it's not taken into account like the model. We just assume that they will still be there.
Yeah, the question is at which time scale you are working at, right? I think the model applies at long time scales when you do some hypothesis on the global structure of the traffic, and not to something that is dynamic and will react to the variation of the delay or the variation of the traffic, right? If I understand correctly.
Yes.
I mean, it may adapt for the two of them. It seems that it fits better the fact that you will analyze, for example, what is the relevance of making an alliance instead of another. At this level of decision, it thinks that it fits very well.
Yes, sorry. Actually, yes, that's... It's true that we have assumed, for example, that for some reasons, maybe that we haven't discussed here, the alliance is formed. I didn't discuss at all how that is. So yes, it makes sense that they are not going to split in the short term. That makes sense. Then, if it's targeted more to selling for the final user or to big customers, I think that could be argued in both kinds. Myself, I'm more in the side that it would be for big users like us.
Let me put it in other words. I understand understand that the alliance is fixed, but then think the whole let's suppose we are one of these players,
Yeah.
and you have to
Bias.
decide.
Bias or the nodes.
Well, no.
Okay.
You want to decide whether to make an alliance with one group or with another group. Then at this level of decision making, it seems, from my point of view, that this type of analysis fits very nicely. You assume some average traffic, some average delay that represents each node, and then you take a more strategic decision of whether to join an alliance instead of another. And if you move down into the time scales, and you go till the level where end users will ask for a video, it seems that it's not such an excellent fit, right? What do you think? And of course, there are many intermediate time scales to consider.
Yeah, I actually see it in two steps. First one is in the moment of setting up the alliance, and that's true. There we need some idea, of the average revenues that they are going to get, in order to see if the alliance makes sense. So that's all as well related with that stability idea that I was saying. If we can see that in an average situation, they could have some guidelines to decide forming an alliance or not, besides other business relations that they could have. So, yeah. However, with the second step that I said I see in the two steps is when we are going to sell. If we are selling in this rapidly dynamic scale, we could do it, but yes, provided that the big numbers keep there. I mean, the ones used for forming the alliance. Maybe the user should be taken into account, or the willing survey should be also model, or real evidence should be.
But the feedback on the state of the system,
Yes.
on the delays, etc. So
A question also about with this equation. There are some information that operators maybe do not want to provide to others. I think QoS, for example, if it is a cost function, if it depends on the ISP, it may not want to give this information. So how do you manage this confidentiality aspects in such a case?
Okay, that's interesting. And yeah, actually there are two things. First one, it's the big framework of alliance that some trust is assumed. This trust could be among the members of the alliance, or it could be a centralized entity that will gather all the information, and we all trust that this entity will not disclose the information. Another nice part of this is that as we are solving it distributedly, the allocation phase, not the revenue sharing, but the allocation phase, actually these values, which are these values, which concern the delays and the capacities, are accumulated in the way back to the network, to the source node. So we are losing the information of each, or the contribution of each of the nodes in the node. It's true that in the end, for performing the revenue sharing, we are too trusting in this centralized entity that knows the capacities and that can perform this, or the revenues at least of each. I don't know if that answers.
How do this coalition form? Because the problem with coalition again for me is, okay, try everything and then choose the best. How do you manage to arrive to the good coalitions?
Okay, that's also an interesting aspect that, yes, we have started from saying, okay, the alliance is fixed. I think that could be, it's a really interesting problem to discuss, and we could also think about some game theory approaches. But in my opinion, it would mainly be given by decisions in a higher level, like business decisions, or this big provider will talk with this other one to reach this and this other region, and if now figures make sense in the big scale, that's kind of my opinion.
thank you very much.
Thank you.